So let's now see how's clustering evolving in the universe, and that introduces interesting phenomenon called galaxy biasing, which I hinted already. And what's meant by this is exactly what we implied, that you can observe structures in light, some differential density amount, excess or deficiency divided by the mean. So the relative variations in density of light are somehow related to the relative variations in density of mass. And the simplest thing to say is there is just direct proportionality, and if constant is equal to 1, then they're fair tracer. So that little constant b is called the bias factor, and it turns out that, in fact, b squared is the number that connects the observed two-point correlation function with the light, with that one of the underlying mass. So because b could be different, like if galaxies are clumped more strongly than the mass, b will be greater than 1. That's what proportionality is, right? And say b is 2 or 3 or 5, then galaxies would not be a fair tracer of mass. They'll be a biased tracer of mass. They would be favoring the densest spots. And so that was the basic idea. And it turns out that some of that is actually happening. And the simple model for this is, let's assume that in a very distant universe, when you start forming galaxies, you require them to be above certain density threshold for stuff to fall together and ignite star formation. Now, remember, density field can be interpreted as a superposition of waves of different wavelengths and amplitudes. So you have small waves riding atop of large waves. Now, if you impose a threshold, then you're naturally going to select first the small peaks that are riding atop of big waves. And so in this picture, first galaxies will form in first clusters, and then star formation will spread down. An equivalent of that would be, say, if you look at the snow line on planet Earth, right? You will see that it's only the peaks of the highest mountains that are covered. Or even if you were just to say, let's ask, where is this Earth's surface as a function of elevation? Well, first you see just a whole bunch of correlated spots in Andes and Rocky Mountains and Himalayas. And then as you lower down the threshold, eventually all of the surface of the Earth is encompassed. So with galaxy formation, the idea is that you start with the densest spots and then eventually spread further out as you have more time. And this is an illustration of this from a numerical simulation, one of those simulations of structure formation, showing both what gas and stars do and what the dark matter does. And people who did simulation know exactly what particles are, and then they ask, okay, what are the 1 sigma deviations from the mean? And cut. What are 2 sigma, 3 sigma, and then they run out of volume. And you can see the higher threshold of contrast you demand, the more clustered will those spots be. So this also explains why clusters of galaxies are clustered more strongly than galaxies themselves, which was very puzzling until Nick Kaiser came up with this idea. All right, so does bias depend on something? Well, remember, two-point correlation function was different for bright galaxies and faint galaxies, and red and blue and so on. And that is simply reflecting a bias factor. The more luminous, more massive galaxies are higher bias factors, so they look more strongly correlated. And so this has now been measured and seems to fit theoretical models just fine. Okay, what about evolution in time? Well, generically, you expect that clustering grows stronger in time because the density field slowly collapses upon itself, galaxies, dark halos coagulate, accrete more. So you expect that there is less clustering in the past than there is here now. Right? So you expect weaker clustering at larger edges as you go far away. And sure enough, that is what you see. This is plot of the strength of correlation function on the sky as a function of depth in survey. And the deeper you go, the weaker it gets. This is what you naively expect. And this goes all the way out to about redshift of 1, when the universe was half its present size. But then, beyond that, something weird happens. It turns around. Then, as you go deeper in the past, clustering seems to grow stronger, which makes no sense whatsoever, because you couldn't just collapse things and then let them fly apart. So how is this possible? And the answer is the bias itself evolves. This was already sensed in these redshift histograms from deep pencil beam surveys. I told you how it seemed to be encountering same kind of structures no matter how far we go, walls, filaments, and so on. And now we think we know why this is. And so look at this. Consider, say, just behavior of the highest contrast fluctuations, 5 sigma fluctuations. Those will be the densest, and they will start collapsing first. And those will be the first one to turn on galaxy formation. Then you go to lower thresholds, say 3 sigma fluctuations. They'll be following, but with some time delay, and so on, down to lowest fluctuations. So if you impose a threshold, then the highest peaks would reach it first, and those are the only galaxies you can see. So because those are the most biased spots in the density field, you'll see that galaxy clustering was stronger in the past. Instead of that, you're not actually seeing behavior of the underlying mass. For underlying mass, they all grow in time, only grow in time. But the illuminated peaks, which ones? That changes. And that explains the observations. And so now we can ask the question, how is that evolving in time? Again, from very deep surveys. And you can see that near us, at low redshift, bias factor is about 1, just as I told you before. But then as you keep going to higher and higher redshifts, it keeps climbing. And in fact, when time galaxies were forming, maybe 5 sigma peaks or 6 sigma peaks were the ones to first go non-linear and ignite.